Morning. Thank you so much for inviting me. I'm going to be talking about one of my favorite things in the world, which is the Vredefort impact event. Now, before we start talking about Vredefort, I want to give you a little bit of background on what's happening with these massive impacts. Now, every one of these dots on this graph is representing asteroids that we know where they are. Okay, good. Now, what we're looking at here is a map of the solar system. The sun is in the middle, and each one of these circles here represents the planets. So this is the orbit of Earth around here, and you can see a lot of those asteroids are crossing the orbit of Earth. And these objects from space bump into the Earth all the time. There we go. So these things happen basically every day. Over Malmesbury a little while back, in the daytime, there was a fireball that was visible over a farm. People are talking about these things exploding over Hermanus as though it's an indicator of the end of the world. And just a couple of months ago, there was a daytime explosion of a fireball over Cape Town. Now, each one of these types of events is something small. To give a sense of scale, something about this size was probably what's going through the atmosphere to make those fireballs, maybe even smaller. Now, we're going to be talking about some bigger meteorites that have come down, and I thought I would start by talking about the first meteorite that was ever discovered in South Africa. It's known as the Cape of Good Hope meteorite. Now, it was discovered back in 1793, and you can see it sitting on the desk next to this nice fellow. This is a fairly large iron meteorite. Originally, it was 140 kilograms, but now it has been distributed around the world. So this is one of the larger samples that still remains. This is in Vienna, Austria, provided to me by my friend Ludovic Ferrier. And he gave me some information about this meteorite. So the Cape of Good Hope meteorite, originally from South Africa, meteorite traders have sent it all around the world. So you can see it's in a bunch of different countries, in a bunch of different sizes. And in Vienna, they have 5 samples that they acquired at all different times. So this is a fairly large meteorite, and it attracted a fairly large amount of attention. And so traders have split it down and traded it all over the world. That's what one meteorite can do. Now, the Cape of Good Hope meteorite has another interesting aspect to it. In 1814, a large piece of the Cape of Good Hope meteorite was forged into this sword and presented to Tsar Alexander I of Russia. It's inscribed with a note that mentions that this is metal that came from the skies, and this is given in recognition of the peace after the defeat of Napoleon. Now, Cape of Good Hope meteorite it's a pretty big meteorite. But if you have an interest in meteorites and you would like to go see a really big one of the largest meteorites that's intact you'll find up in Namibia, this is the Hoba meteorite. Now, it's about 50 tons in weight. The general story is that the reason why there's a shrine to this meteorite is that it was too heavy for anybody to move. So that's about 3 meters long and about 1 meter thick. And that's a really, really massive meteorite. What happens if you get a little bit bigger than that? Well, things bigger than that tend to cause some events. So this is in Chelyabinsk, Russia, in 2013, about 10 years ago. Some of you might remember this event. So that was an asteroid that was about 12,000 tons. So quite a bit bigger than the Hoba meteorite. And when it passed through the atmosphere, it exploded and sent a shock wave through the atmosphere. That shock wave damaged about 3,000 buildings and injured about 1,000 people. And that's a moderate-sized rock coming from space and did quite a lot of damage. Now, what happens if we get a lot bigger than that? Well, if we get up to about a 30,000 ton meteorite, then you get a real impact crater. So if you go up around Pretoria, this is the Salt Pan Pretoria or the Tswang impact crater. This was formed by a much larger object about 200,000 years ago. And so this is up in the scale of about 30,000 tons. Now this is a lot of times what you think about if you think of an impact crater. You think about this bowl-shaped type of feature. This is really the classical picture of what this looks like. So how big is that really? Well, recently the DART mission by NASA visited the asteroid Dimorphos to try to see if it could change its path, which they did successfully. And it looks sort of like that. That's sort of what the Tswang meteorite would have looked like while it was floating in space. Now, in terms of how big it was, you can sort of imagine one of the buildings underneath Table Mountain. That's about the size that the Tswang impactor would have been. So, what's going on when we have these big impacts? Why does it make this bowl-shaped crater? Well, when the projectile comes in, it comes in at really high velocity, in the order of kilometers per second, so much faster than we drive on the highway. When it hits the ground, the impactor smashes into the ground, and usually with a large impact like this, the impactor is vaporized. A lot of times people ask, what happened to the meteorite? Well, the meteorite becomes dust in these large impacts. It's not something you can find. When that happens, it sends a shock wave through the ground, and that shock wave causes the rocks to break and to melt and even to vaporize. The process of all of that rock being excavated leaves you with that circular bowl shape. And it also sends material flying for a long distance. We're going to talk about all of those aspects here in a bit. So the Tswang impactor was pretty big, building-sized impactor. But what about a really big impact? What if instead of one of those buildings we had Table Mountain impacting? Now Table Mountain, for our purposes, it's about 1 kilometer tall, and it's about a 10-kilometer circumference, or an area of about 10 kilometers. Now that would give you a really big impact. But what if you doubled it? And then you doubled it again. And then you doubled it again. And you add a few more Table Mountains for good measure. That gets you up to about the scale of the impactor that made the Vredefort impact. It was a big event. So we can't really make that in a laboratory. If we tried to make an impact that big in a laboratory, it would be pretty bad for everybody. But what we can do is we can make computer simulations. So what I'm going to show you now is a computer simulation of what happens when you have an impact on this scale. Now, the first thing I want to note is that we're only looking at half of the impact here. It's symmetrical, so you'll see half of the crater being formed, but you have to imagine the other half. This circular thing here, that represents the impactor. It's going to be moving straight down into the ground. This line here at 0, that represents the ground surface, and everything below that is the Earth. And we notice the scale here is in kilometers. So this is 20 kilometers below the ground, and this is 20 kilometers above the ground. So I'll play this simulation for you, and then I'll talk about it. Now, one other thing you can notice here is that time is moving in seconds. So we've moved about 5 minutes from the time of impact at this stage. This runs to about 10 minutes.
Can you replay that?
Absolutely.
Please?
So let me start off. I'm going to walk through this a little bit slower if I can catch it.
Yes. One.
Now, we start off and you can see that there's no time at all before the impactor is just vaporized. It immediately merges with the ground. Now, we step forward a bit more and we see this cavity opening up. We have this hole in the ground. This is the crater, so to speak. That goes about 40 kilometers down in the space of less than a minute. Then it rebounds, just like if you throw a rock into water, that'll splash back up. That rebounds and it rises up to about 30 kilometers above the pre-impact ground surface. So it smashes everything down, everything rises up rapidly, and then things start to settle back down. Things collapse back, and then we get the final form of the crater. Now, that does a lot of damage when it happens. It damages those rocks, and it's in a very wide radius. To imagine what this would have looked like right after the impact, we have to go to the moon. So this is the Schrödinger crater on the moon. It formed very similarly to Vredefort, very similar scale. And we can see some of the features of this. On the outer edge of this, we have a crater rim. You'll notice this is not a bowl-shaped feature. It's not bowl-shaped because those rocks in the middle rise back up after the impact occurs. We do have a defined crater rim. We also have this inner ring of hills that we call a peak ring. And then we have all this flat area inside of the crater. That's the melt chute, the molten rock. It's almost like a pool of lava that settles in the middle of the crater. And we also have these fractures inside of that. Now, craters like this, we only have a couple of examples of those on Earth. The most famous of them is the Chicxulub impact structure. Now, the Chicxulub impact structure formed relatively recently, only 65 million years ago. It was of a similar scale to Vredefort, maybe a little bit smaller, but it's very different in that it is completely buried. We only know about it from geophysical investigations or from drilling down to examine the rocks. We don't have any of it exposed on the surface. Now, what makes this impact so famous is that it marked the end of the dinosaurs. And it represented a really large changeover in life. Now, to give a sense of the scale of what this was doing, this is a map that shows all of the material that was blasted out of the Chicxulub impact that's been found and studied. And you'll notice some of these up around the border of Canada. The impact itself is down in Mexico, but up around the border of Canada, there's a site where they discovered fish fossils. So you can see this is a scan of these fossils. You can notice it looks sort of like bones there. That's because it's bones. And down here, they've added some color to it so you can see what's going on. Now, the purple is more or less representing the bones of the fish. And all these green things here that look sort of like buckshot, that's material from the Chicxulub impact that was shot into these fish from over 1,000 kilometers away. Just like shooting fish in a barrel, except it was in a lake and it was an impact. So these are really massive events that have global consequences immediately. But we want to talk about how these things are affecting us today. So for that, I want to put things on a little bit of a timeline so we can have a good idea of what's going on through geological history. So the Earth is about 4.5 billion years old, 4,500 million years old. We live now on this side. The oldest rocks and the oldest evidence of life is about 4 billion years ago. Now, when we start getting fossils of hard parts of animals, that's about 542 million years ago. So anytime you see anything about fossils, that's within the last about 500, 550 million years. The dinosaurs, lived from 65 to 250 million years ago, relatively close in time to us. They were killed by the Chicxulub impact event. Now, the oldest rocks in South Africa are pretty close to the age of the oldest rocks in the world, but then you may have heard about the Witwatersrand sediments. Those were deposited between 2,900 and 2,700 million years ago. And then after that, we had the Transvaal sediments, another rock unit you might have heard of. After those were deposited, long after that, then we had the Vredefort impact event. It was, in a way, the midlife crisis of Earth. Pretty close to the middle of this timeline, 2,020 million years ago, that's when Vredefort occurred. Now, one other thing I'll highlight is the Karoo supergroup. If you've done a road trip across South Africa, you've driven on rocks of the Karoo, that occurred, it overlapped in time with the dinosaurs. Much, much, much younger than the Vredefort impact. So finally, let's actually look at what Vredefort looks like. So if you're not familiar, it's located just south of Johannesburg. One of the key things that you can see this line of hills here in a semicircular shape. This is a map view, and the colors on there represent the geology. So there's that semicircular ring of rocks. That's the Vredefort Dome, and that's what you might be most familiar with. But that does not represent the size of the impact crater. That is the remnant of the peak ring of the impact. If you remember from the picture from the moon, that's the ring of hills in the middle of the crater. The original diameter would have been about 300 kilometers. So 300 kilometers represents the area that was directly damaged by the Vredefort impact event, either during the impact or immediately after. The rock units that are represented here are more or less the ones I just showed you. There's the basement granites in pink there in the middle. We have the Witwatersrand supergroup, and then the Ventersdorp lavas next to the granites. And then moving out, we have sediments of the Transvaal supergroup. Those were mostly the things that were affected directly by the impact. Now, 2,000 million years is a long time. And in that amount of time, we went from this original shape of the crater where we had this uplift in the middle, we have this peak ring that formed on the edges, this uplift of the rocks, this melt sheet, that was a pool of lava across the top of the impact crater. All of that has been eroded away. There's been roughly 10 kilometers of erosion that have occurred since the Vredefort impact happened. So what's left for us is a very deep cross-section that lets us see the architecture at the bottom of one of these giant impacts. So we have a few different things that we can look at that really tell us beyond any reasonable doubt that this had to form in an impact and not through any other process. So one of the things we have are impact melt dikes. So even though the melt sheet has been completely removed by erosion, we still have these melt dikes that poured down from the melt sheet and formed rocks that look a bit like this. So you can come look at this after the talk. This is a piece of one of these impact melt dikes that in some cases still carry signatures of the impactor. There's also rocks that didn't come from the melt sheet, but that melted in place. These are called pseudotacholites. It's a terrible word, but it's the one that's used. And so you can see here, this is a quarry for granite, and the granite is nice, pretty, and pink, but there's all of these black lines running through there, these black zones. That's where the granite was melted by the passage of the shock wave through these rocks. This happens in a lot of rocks around Vredefort. You can see in this sample, for example, there's this black line running through here. That is also a smaller pseudotacholite. Another line of evidence that we have that this was an impact, we have shatter cones. So you can see these cone-shaped breaks on this surface of rock. These are shatter cones. This is where the shock wave passed through the rocks very rapidly and broke them in almost a plume-type shape. We'll do that later. We'll do it later. So I have here an example of a shatter cone. These are in a shale. This one is a shatter cone in a lava from the inside of the impact crater. And when you look at it, you'll be able to see this fan shape break that runs across these rocks. This is a fracture pattern that only happens when you have these hypervelocity impacts. Now, all of those are fairly convincing for different reasons, but the other thing that we have are shocked minerals. Now, if you are familiar with geology, you know about zircon. Zircon is a very tough mineral. It's hard to do anything to a zircon. But this particular zircon, if it was a normal one, then when we made this map of it, we had to use some fancy machines to make this map. If it was a regular zircon, the whole thing would be the same color. All of these orange and red lines you see running through there, that's where the actual crystal lattice of the zircon was deformed by the passage of the shock wave. So it's causing effects on the large scale and it's causing effects on the mineral scale. So with Chicxulub, we saw that it was blasting material all over the world. Is this the same with Vredefort? Yes. So we found ejecta, the material blasted out from the impact. We found that in two distinct locations. One is in Russia and one is in Greenland. So these blue dots up here represent where we found the ejecta from Vredefort. At both sites, it looks about the same. You have these little circular and teardrop and dumbbell-shaped things. These are little droplets of molten rock that went flying through the air. They take on these shapes because they're spinning in the air, and the sphere is the best shape for spinning through the air. These are about 1 millimeter across or less. In Greenland, where we studied these, we were able to examine the rocks below and above this spheral layer. And these were all rocks that were laid down by the ocean, at the bottom of the ocean. And we found the red line is what the sediments look like above the spherules, and the blue line is what the sediments look like below the spherules. It's suggesting that when the impact happened, it changed the chemistry of the ocean. So that the rocks that were being precipitated from the ocean after the impact had a different composition than the ones before the impact. Okay, now everything I've said up to this point is basically academic. And it's all very interesting, but why does it matter? How does this affect us today? Well, let's look at another map of Vredefort. So you can see in this map, what this map is essentially showing is the area of damage of the Vredefort impact. I mentioned about 300 kilometers, that's about the diameter of this map. But even though that's what this map is showing, that's not what this map is. This is a map showing us where the gold fields of the Witwatersrand Basin are located. You can see these things indicated in blue, all in a semicircle around Vredefort. Those are all the gold fields. That's where the gold mining actually is taking place. Is it a coincidence that Vredefort is in the exact center of the richest gold field in the world? No, it is not. So what's actually being mined at these gold fields? Well, they're mining this. This is a conglomerate. It's usually described as a quartz pebble conglomerate. These are rocks. The original rocks were laid down in sediments. As I mentioned, 2,900 to 2,700 million years ago. That's what these are. This is like stream gravel. And you can see a lot of shiny things inside of these rocks. This is not gold, this is pyrite, fool's gold. But the gold is actually inside of the pyrite in most cases. This is the richest gold deposit on Earth by a wide margin. About 1/3 of all of the gold ever found in all of human history came out of the Witwatersrand deposits. And they're still mining it now to great effect. So what did Vredefort do to affect this gold? Well, these were rocks that were living very happily deep under the surface of the Earth when the impact happened. When the impact occurred, it uplifted those rocks. So we can see here a cross-section. On this side, on the right-hand side, we're looking at the middle of the Vredefort structure. On the left side, we're looking at the periphery of the Vredefort structure. But this is where the Rand anticline is. This is the area where a lot of the mining is taking place. You can see there's lots of faults, lots of fractures there, cutting through these rocks. And you can see how these rocks that were deeply buried were turned vertical and lifted up to the surface. Now also on the other side, you see there's a lot of faults that are actually pushing the rocks up. On both sides, the uplift of the rocks is because of the impact. So shortly after the impact, it would have looked something like this, where you have all these molten rocks sitting on the top of the impact, but all of these Witwatersrand rocks, indicated here in yellow, they were brought up near to the surface, where they could eventually be discovered. Now the modern mining is mostly happening near the Rand anticline, on that edge. Those are rocks that were brought up by the impact. But if we look on the other end, we should see the same rocks. And in fact, we do. If you walk around the hills in Vredefort at the right spots, you can find a lot of these old mining adits. These were dug in the 1800s by people who understood that these were the same gold-bearing rocks. If you go to look at them, you see these are the same types of quartz pebble conglomerates as you get deep down in the mines around Velkom. These were not mined too extensively because in the middle of the impact structure, there's a lot more faults. And so these rocks are much more displaced, and it's hard to follow one seam continuously. So the miners in the 1800s gave up. Some people came back and suggested they could just strip mine the entire hill and get the gold out of it, and fortunately they were told, no, you can't do that. So when the impact lifted up these rocks, it lifted up the Witwatersrand rocks in this area around the impact. It caused this arc of the rocks up towards the surface where eventually they could be discovered and they could be mined. If they had not been brought to the surface, then they would still be buried far below our feet. We would never know about them, and the largest gold deposit on Earth would be undiscovered. Now, what Vredefort did was not only uplift the rocks of the Witwatersrand. In the middle of this model of the Vredefort structure, you also see the granites in pink that are being uplifted. Those granites have played a role in Vredefort history, and they're also rather important right now. I'll talk about that in a moment. So first, what these granites were significant for was dimension stone mining. So from about the 1950s to the late 1980s, early 1990s, there were a lot of these quarries that were dug that were sold for dimension stone, or decorative stones. These were used in a lot of places, not only in South Africa. You can see a lot of these stones in OR Tambo Airport to this day in Johannesburg. And you can see the cut faces of these quarries. These were dug out because they were beautiful and unique stones. Now, this is mostly inactive, but if you're still interested in buying a block of Vredefort granite, it is still available. There are still some small sellers that are selling these blocks. Now, today, these quarries are mostly inactive, but they do provide an excellent place for training geology and for helping students to understand what's going on with the actual Vredefort impact. They've also become a spot for adventure tourism, that you have people rappelling on ropes and doing adventuresome things in these quarries, and so they've become a tourist destination. Now, these things are all nice, but the granites did something else that's really rather interesting and has only been understood very, very recently. So here's a cross-section of some of these granites. Now, just to make things simple for us, on the bottom we've got granite, and on the top we've got these very young rocks of the Karoo. Now, as I mentioned earlier, the Karoo formed way later than Vredefort. It was not involved in the impact at all. And in fact, there's been no deformation of the rocks of the Karoo at this site. So these are just flat-lying sediments. Shales, sandstones, these types of things. And you may have heard some about the natural gas in the Karoo. Well, some of that exists in the rocks of the Karoo right over Vredefort. But there's an interesting aspect to those. You see, the granite, like all granite, has a lot of minerals inside of it that contain uranium. Now, uranium, of course, is radioactive, and as uranium decays, it undergoes alpha decay, and that releases a particle of helium. Because the granite under Vredefort has been so broken and fractured by the impact, it creates conduits that allow that helium to travel up. And that helium would go all the way up into space, except it runs into the rocks of the Karoo. And it runs into these natural gas deposits. And when it does, it gets trapped. And as a result, it makes a concentration of helium in the rocks of the Karoo, but only in the spot specifically where the Karoo is above the granites of Vredefort. So this is an almost unique deposit, and it's become understood to be one of the richest helium sources that's been discovered. And the reason is because with all of these fractures, it creates a massive surface area of granite that's producing this helium. And the helium is being concentrated in very high quantities within these natural gas deposits. So in January this year, Renergen has produced their first helium, and they're expecting it to be one of the larger helium deposits on Earth. This is really very modern and not entirely understood, but it is absolutely a way that this impact is still affecting us. So, I've talked about gold, I've talked about helium. I'm going to talk about something else here. We're going to step outside of the Vredefort impact itself. So again, I've got a map view. You can see the hills of the Vredefort Dome. I've marked the 300-kilometer diameter of Vredefort. And I mentioned earlier that we found material ejected from Vredefort in Greenland and Russia. Well, we found material ejected from Vredefort a little bit closer to home as well. You see, when the impact happens, it blasts material out and creates a curtain of ejecta, and it creates a zone of proximal ejecta. What that looks like is a breccia, angular blocks and fragments of material that can be quite thick. In fact, at 500 kilometers distance, you can even have a 100-meter thick layer of this broken material from the impact. Well, I've indicated some area in purple there on the left-hand side of the map. Now that corresponds to some of the rocks inside of the Maramane Dome in the Northern Cape. So if we look at those, these are the rocks in purple here. You can see this almost a letter D shape there. That's the Maramane Dome. And that is South Africa's richest producer of iron and produces massive amounts of manganese as well. Now, the way that that iron got there is a complicated story. I'm not going to go into it in full here. But what I will talk about is the Maramane Dome itself. You can see these are rocks that have this anticlinal form to them, but they've been cut off at the top. Now, so you can see there the anticline form. You have all of these rocks that were deposited and then bent, and then you have these sediments that were deposited on top of that. Well, to put that into a little bit of a perspective, we have the basement granites, we have the Fintersdorp lavas, we have the rocks of the Transvaal supergroup that I mentioned on the timeline earlier. Those were all tilted. They were all bent into this anticline form. They were uplifted. But that happened before the Vredefort impact. That was an event, a geological event, older than Vredefort. This is quite a long time ago. That was then exposed on the surface and eroded down to give a new land surface. And then there were sediments deposited on top of that. Now, a lot of these sediments are host to the iron mineralization, at least in part. Well, when did that happen? We were looking at the rocks and figured out that those sediments were deposited at the same time that the Vredefort impact occurred. So we went and we looked at them. And we found a lot of rocks that look like this. You have these broken angular fragments, sometimes cross-cut by seams of iron, but there's no change in the rock there. That's still the same breccia. It's just where the iron came through and replaced everything. And we got to wondering, how did that breccia get there? So we started looking at it, and we started looking for shocked minerals. And what we found, in fact, you have these quartz grains that have these planes cutting through them, sometimes several of these sets of these planes cutting through where the minerals have been deformed by the passage of a shock wave. So we figured out that these breccias in the Maramane Dome, in the Northern Cape, 500 kilometers from Vredefort, they are related to the Vredefort impact. They formed at the same time as the Vredefort impact occurred. We also found at the top of these deposits that there were these accretionary lapilli, these ball-shaped features, which we know from other impacts are happening because you have bits of ash from the impact that are sticking together into this ball shape. So we think we have a new understanding of how these iron deposits formed. Not the iron itself, but the host rocks of the iron. So before the Vredefort impact, we had the land surface exposed. Then the Vredefort impact occurred, and it sent this breccia tumbling over the land surface. That covered the whole land surface and was exposed on the air. And then later, there were hydrothermal fluids that came through and altered that to have iron, and eventually gave us the iron deposits of places like the Sishen mine. So there's at least 3 major economic deposits in South Africa that were directly affected by the Vredefort impact. Now, on top of that, Vredefort is just a nice place. And it's been designated as a World Heritage Site by UNESCO, not only for the interesting geology, but also because the uplift of these hills around the Vredefort Dome creates a microbiome and creates an environment of special vegetation and a unique area for adventure tourism, rafting on the Fall River, or climbing up mountains, going on hiking trails. It's home to the largest olive grove in the Southern Hemisphere on the El Dorado farm. It's a place to go for hikes, for relaxing, and is a frequent spot to be visited. Not only is Vredefort a special place, people have known that it's a special place for thousands of years. This is the Daskop farm. This is one of the impact melt dikes that came down from the melt sheet. And if you walk along that particular dike, you'll find carvings like this. that were carved as long as 3,000 years ago by the Quaison people, probably the San people, that were migrating through the area, who didn't understand that this was an impact, certainly, but they certainly understood that it was a special place. So, I will contend that the Vredefort impact still impacts us today. It uplifted the world's largest gold deposit and made it discoverable. It created conditions for what may be one of the largest concentrations of helium in the world. And it at least contributed host rocks to one of the largest iron mining districts in the world. It also produced decorative stones, it created a microbiome, and it created an area that we can enjoy and that has been enjoyed by people for a very long time. Thank you.
Okay, I'm sure there's going to be questions and discussion from this audience and the Zoom audience. So, who wants to?
Great talk, thank
Who
you.
wants to kick off? I know Keith is biting at the bit.
Sorry.
Yeah.
Am I interrupting?
Yeah. No, go for it. Right.
You mentioned the vegetation. Is that quite a unique area, vegetation-wise? I don't know how, did I hear you correctly with?
Yes, it is a microbiome. So it is a farming district that is distinct from the surrounding farming districts, I can say that. A lot of citrus plants and nice things grown there. I'm not going to try to go too far into the plant side because that's not my area.
No, that's fine. Thank you.
Okay, if I can just kick off, Matthew, just starting with the geoheritage and education, how active is it? Is that through the museum that the Oppenheimers helped fund in Paris? Or, I mean, we know that there was a super large state building which built, which has never been used because it was badly built.
Yeah, now you're getting into a sad topic here.
No, I know, but just...
So there was a Vredefort museum that was built that had a grand opening and the next day was closed forever. I think that's an accurate summary of the events. And that, I think it was in 2008 it was supposed to be opened. The last time I visited, the building was just crumbling.
Yeah.
The Paris Museum had a very nice display of artwork by Maggie Newman that was up in 2019, but when I tried to check back more recently, the museum had been closed. And I do not know if it's been reopened at this point. I haven't been up in recent months. Yeah. But the museum has always been struggling. It's never had much. There was a very active discussion about making some road signs and some low-tech information centers around Vredefort. That discussion was mostly going on before COVID, and several of the people that were involved in that project passed away. And it's been more or less at a standstill since then, as far as I'm aware. So a lot of the public education, much more is needed to be done. The landowners are the landowners there know they live somewhere special. Yeah. They want to communicate that it's somewhere special, but it needs a little bit more effort.
Yeah, no, just it's a very important point, and it goes back to what we've been trying to do here in the Overstrand with the OGG. And there's absolute world-class facility and place and geological unit, but it really hasn't reached its true potential. I know Stuart Clark, for example, was talking to one of the farmers about taking over a farmhouse. And it just goes to show, you know, that we just undersell our amazing geology, and something that, you know, we also learn from, and it's, for me, the success and the future is getting young people involved, and we're very lucky to have people like you and the support, for example, of Oscar and his group at MinROM. But let's move back to the technical stuff. Henny, have you got a question there?
Well, I think he had a question.
Okay.
I'd like to go last.
Okay, no, I know what you're getting to. All right.
Loud when you speak, please.
Very informative, interesting, and well presented. Thank you.
Yeah.
Have you done any work on the impact that the dome had on the Bushveld Igneous Complex in the Zimbabwe Great Dyke? I'm glad this was asked.
And then don't forget Palabora. You know, that's very interesting there. There are a whole lot of major events around this sort of 2 billion year age.
For some reason, 2 billion years ago is the most interesting time in South Africa's history. And
Us as well.
so this specific question is about the relationship between Vredefort, Bushveld, and the Great Dyke. Now, those are all in a line geographically.
And Torpsburg.
And more things as well. Now, for a long time, the dating on Vredefort and Bushveld was a little bit uncertain. And there was a suspicion that either Bushveld was also an impact or that Vredefort triggered Bushveld. And now we know that Bushveld was emplaced before the Vredefort impact occurred by a good 40 million years. In addition to that, some of the stringers of the magma from Bushveld reach all the way into Vredefort and are shocked by the impact. So the magma had to be already crystallized before the impact occurred. Now, there is some deformation on the edge of Bushveld that looks like maybe it's related to the uplift of the impact. That's a little bit unclear. The Great Dyke is certainly completely unrelated to Vredefort. However, if you start going on Google and looking for information about Vredefort, you will find some enterprising chap has written a book where he says that the Vredefort impactor came in at Vredefort, went under the ground and blew up and made Bushveld, and went further underground and blew up again and made the Great Dyke, and it killed so many animals it made the Karoo supergroup. And it made all the kimberlite pipes come up and made all the diamonds. You'll find that on the internet. It's nonsense.
That's not your publication.
No, that's not me. But that's another aspect of the geoscience education about Vredefort. If you're a person that's interested in Vredefort and you start Googling, that's one of the texts that's publicly accessible that's not far down the list. And it can steer you way off in the wrong direction if you get into that.
Okay, the next question is about Renogen, and where does that helium come from? Is it genuinely the granites, or is it the decay of the uranium and the Wits?
Right, so my understanding of the stratigraphy, exactly where those are positioned, is that it is the uranium from the granites. As far as I understand the stratigraphy there, it is granite and Karoo sitting on top of it, not granite and Wits and Karoo. So all of the uranium involved should be from the granite, and it should be just by the decay of those radioactive elements in the granite with the faults siphoning that in. Now, when they do the estimation of how much helium is trapped there, what they're looking at is the age that the Karoo rocks were deposited, and then they know the half-life of uranium. And then it's some relatively simple math to just say, if you have this much time and you have this half-life, how many particles of helium are you generating? And so they make the calculation in that way.
Okay. All right, any more questions in the room? Keith?
Right, Matthew, I've spent my life looking at the Wits.
And how old are you, Keith?
About 7 million years old. The youngest dinosaur. One of the things that I am starting to believe is our history there. When I started this Wits was in NASA, then I was part of the great Anglo-American Basin Analysis team, and most of the work that I did showed conclusively it wasn't NASA. Okay. But I've got a problem with that model we have as well. Since then, I've done a huge amount, and then I retired, but I've still got all the data, and no one has seen it. No one's ever going to get that data again, because it's impossible to get. I took 2 kilometers of raised line of samples, lithological sampling down there, and analysed them up to 68 elements. And boy, what has come out of that is a bit strange. First of all, the rare earth profile of that carbon seam zone is completely different to the rest of the sediments. It's the same as your rare earth profile over there. The heavy rare earths are hugely interested in the carbon seam. Then what we did was we put that carbon seam in a scanning electron microscope with cathodoluminescence set up to pick up secondary quartz. And there's a shock plane in that narrow carbon seam.
Oh, wow.
We showed it to the second section here.
Yeah. Well, we don't have a microscope here.
No, but you can see it in the hand specimen.
Okay.
You can come and have lunch with
we'll
Keith.
definitely, we definitely.
It is there.
Oh, fabulous.
I'll show it to you. And what we've done is we've taken it apart. I've actually had the thin section of the synchrotron in Australia. We never finished the work as nice as things are. You'll go into other things before we finish anything. But the selenium we can find and the hafnium is not related to the zircon. The other thing is beneath this carbon seam.
Keith, if you're going to be talking, come up to the
Come
okay, we've got a Zoom audience.
Okay,
They can't hear what you're saying as well.
Okay.
Yeah, and quick summary, Keith.
Okay.
Come stand here.
On this mic.
Okay. What occurred
Come,
beneath
come,
the
come,
carbon
Keith.
seam is orthogenic zircon. It's so rich in uranium we can't date it. We've had it in the ship. We cannot date it. It runs, if the granitic, the trital zircon runs about 90 ppm uranium, these run at 1000 ppm uranium. These little zircons, and they're in the fluid inclusion trains. In the quartz, just underneath the carbon seam. Now my point is this thing, this event, had to have something to do with it. And the other reason is that Athabasca, which is the other great uranium carbon basin, has got this ring structure in it as well. And the question is why? Why the coincidence?
Yeah. Well, we need to talk more after this.
Yeah.
Certainly, something that I didn't go too much into, throughout the Wits Basin, you find these pseudotachelites. They look a little bit different in the Wits rocks, but you still have these pseudotachelites almost certainly related to the impact itself.
Why that crystal?
Well, okay, there's different generations of pseudotachelites.
Yeah.
And
We got that we know.
this particular sample has two different generations of pseudotachelites. This is one generation, this is a different generation. This one was probably a tectonic pseudotachelite from 2.5 billion years ago. This is Vredefort. And we've demonstrated that in different papers that are published.
So the pseudotachelites have different ages.
So a pseudotachelite is forming whenever you have rapid movement along a fault. It's often called a fossilized fault. And so you can get those with just tectonic movement, and you can get those with impact.
But these ones are far more dramatic than the pseudotachelites on the fault.
Okay. All right. Well, clearly there's a discussion that you two need to have.
What I did want to mention, though, is that I deliberately did not talk about the placer versus hydrothermal origin of the Wits, because in a lot of ways it's irrelevant.
It is irrelevant until you can show that it's possible that something, the ore body is related to that.
Right.
Okay. All right. Any other local questions?
Those small particles that you found way up in was it possible for these particles to actually leave the gravitational pull of the Earth, or would not go that far? So that we can find tracks of the Vredefort somewhere on another planet one day?
Yes, that's entirely possible. So when you have the impact occur, it's almost the same as if you bury a massive nuclear bomb and blow it up. And so material does go sideways, and a lot of it goes suborbital, and those particles were probably suborbital. But some of it is blasted in such a direction that it leaves Earth's gravitational field. So there have actually been cases where rovers on the moon very likely found a rock from Earth, that it's suspected that it's one of these really large impacts launched the meteorite from Earth to the moon. We also know that we have meteorites from Mars on Earth, and the only way we could get a meteorite from Mars is if you had a really big impact that launched it out of Mars all the way until it hit Earth. So it's absolutely the case that as these rovers are wandering around on Mars or wandering around on the moon, they could find a piece of Vredefort.
You think about that. That piece of Mars on Earth, that means the impact must have such an effect. There's so much material that a small speck in space can actually pick up one or two of those bits of rock. It shows the effect of those impacts.
Yeah.
Well, it gets back to the point, Keith, and what Matthew's talked about is we don't realize the amount of energy, that is generated by those events. I mean, it's the same as some of our big volcanic events, and how far that ash goes, for example. And it's all part of this incredibly dynamic Earth. We get excited about what happened a few weeks ago, but that's mild in comparison to a major volcanic eruption, or
If you look at the network of fluvial plugs that run from the east coast to the west coast, north and south, it's incredible. Think of how much heat was in the crust at the time. It was ridiculous amount.
Niels Borslap from Mossel Bay says, thanks for the presentation. Is the creating of a virtual museum not only for the Vredefort geosite, but other sites in South Africa not possible?
Yes. So this is something that we at the University of the Western Cape are actively working on. We are trying to make a virtual tour of South Africa become a reality. We've seen an equivalent done in Norway, especially around Svalbard, where there is a virtual Svalbard that you can visit. We have been busy trying to digitize a number of sites. We've been focusing recently on the area around the Tankwa Karoo for various reasons, one being that we take our students on field trips there, and we're trying to add educational resources for them. We are looking at ways that we can make these types of resources available to everyone, and we also want to make a resource where people can contribute to it. One of the things that we don't want to do, I can go with fancy photography equipment and make photos and videos, and I can make it, but it's then limited to my energy and my efforts. And we want to try to create something that's more open to the community. And we're at very much embryonic stages with our efforts. So if anyone is willing to help make that sort of effort a reality, then we are 100% open-armed inviting you.
Well, again, just to add to that, if you haven't seen it, and just for everyone's interest here, on the 15th of this month, we're having an afternoon visit for everyone, grandkids included, to the Earth Age displays we've just constructed in Harold Porter Gardens with Sandby. And that's exactly, we've been very fortunate that Sandby is a well-established structure. It works, it's well managed, and it was wonderful to work with those people and put up that display. So we have created a display with all the major events, and we must check that we've actually got Vredefort. and we would then be keen, to work with you, because that's, unfortunately in this country, vandalism is a huge problem, and destruction of material. Okay, that's right. So working around that, I mean, we have the amazing Mkonjwan Trail in Barberton, which, as well as it was built, is now also starting to be vandalized, tragically. Yeah, and so we have plans to work around that. Oscar's involved, and we'd love to share, the sort of stuff that we've done with you, and collectively do those sort of things.
That would be wonderful.
Yeah.
Just to ask one quick question, and that is the helium that they mine, is it in the gas form or is it liquid?
Yes. They're pulling out liquid helium, but I guess it's...
Yeah, it's the gas.
It's gas. It's the same as natural gas.
Yeah.
They're pulling out natural gas and separating helium. That's what they're doing.
But go and visit their site, and they've had some fun and games lately, as you probably know, because of over-promising and under-delivering. So they've got a whole lot of very unhappy shareholders. It's a fascinating deposit. Yeah.
Can I make an announcement?
Yeah.
I'm good up front.
I have low battery, so be quick.
That's all right.
So I'll shamelessly take this opportunity to announce in January there will be a summer school in UCT, and there will be 2 lectures on 25th and 26th of January on impact craters. So this talk was kind of rooted on Vredefort, but if you want to know more about the process itself, what it does for the solar system, how it affects the Earth in general, then please come to UCT in January. I believe it is not for free. It's like 200 220 rand for adult and 110 if you're staff, or I'm not sure about the pensioner, but if you happen to be a staff or a student, it is a 50% discount. So yeah.
Is that the geology department?
That's so I'm gonna read the lectures, but it is organized by the University of the
It's
Cape
a
Town.
summer school.
It's a summer school. It's like lectures on different topics for adults.
So it's a
Yeah.
great series, as you probably know. No, and if you send us the info, we'll put it in, advertise it in our newsletters.
Okay. Yeah, I have the brochure for the whole event. Maybe it makes sense to send. Yeah. Thank you.
Okay, shall we wrap up?
I think we
It's
must.
been a great session. Thanks, Matthew, and thanks to your colleague for the additional inputs. A great thing for us, oldies again, is to see young people doing